quality work gone into it. So I'd like to tell you about dynamic stabilization of polar oxide growth, and in particular a prototypical polar oxide, magnesium oxide, in the 111 direction. And this is work that I've done, of course, but in collaboration with Matt Probert at York and Vlado Lazarov, also at York. So I'm going to tell you a bit about polar oxide growth, some of the experiments that have been done and some of the simulation work. I'm primarily a theorist. Some of the problems, and I hope I'll convince you solutions, and a couple of device properties that we're interested in. In other words, what are we going to use polar oxide materials for? Now, I know some of you are theorists, so I apologize that there will be some electron microscope images and a little bit of experiment. Some of you are experimentalists, so I apologize, there will be a little bit of theory. If any of you are chemists, I apologize, there will be science. So why are we bothering? Well, traditional complementary metal oxide semiconductor work has used silicon. And obviously, as we go to smaller and smaller device sizes, silicon really just doesn't cut it anymore. It can't cope with the kind of high power, high switching frequencies that we want. And when you make it nice and thin, you get all sorts of problems with leakage currents and such like. One promising candidate material would be silicon carbide. It's not a massive move away from silicon, but it's much more robust. You can switch it much faster. It can cope with much higher power. But you have some fun when you want to use an oxide for your insulator. Obviously, there's a native oxide of silicon carbide. So we've got silicon dioxide, what we've been using until about 10 years ago. The trouble, of course, is silicon dioxide is really amorphous when you grow it. You have very poor interface control. When you start making it thin, you get leakage. It's not brilliant. So we can really rule out the native oxide of silicon. The native oxides of carbon have even more severe problems. So I'm not aware of anyone who's made a carbon dioxide solid state CMOS device yet. So we have to look elsewhere for our insulators. And of course, we need a nice large band gap so that the breakdown voltage is high. Polar oxides are strong candidates for these materials. So this is the motivation for studying these materials in the first place. What kind of materials are polar oxides? Well, typically they're metal oxides. I hate that term, but that's what everyone uses. So they have metal atoms with oxygen. So zinc oxide, magnesium oxide, these kind of materials, they're characterized by strong ionic bonding. So there's large macroscopic charge transfer between, in our case, the magnesium and the oxygen. And the reason we're studying magnesium oxide is really it's a very simple rock salt structure, nicely cubic in the 001. And it's a prototypical polar oxide. There are no subtleties that are associated with, say, zinc oxide. You can study it experimentally and in simulations very well. So here is my cartoon of magnesium oxide. Magnesium in green, oxygen in red. And this is the 001 direction. And if we rotate that and look at the 111 direction, obviously the 111 direction in a cubic material gives you a hexagonal surface structure. And so here, when we grow it in that direction, we find that the films are not atomically sharp. The quality of the films is very poor. 001 films, fine. 111 films, awful. The problems that you see are that when you deposit it on a substrate, you get roughening at the interfaces, you get facets at the surface, you get reconstructions, you get atomic mixing. What are the problems here? Well, basically the problem is that if we look just at the electrostatics here, we've got alternating planes of positive and negative charges. And if we look at what's happening to the electrostatics, every time I add a bilayer of my material, I'm adding a constant to my electrostatic potential. It's like a parallel plate capacitor. in series. So if I try to grow a macroscopic film of MgO in 111, this potential gets bigger and bigger and bigger and bigger and bigger, eventually tends to infinity. Infinite potentials lead to all sorts of interesting physics that we don't like, and neither does nature. So what we find is that these interface reconstructions, the roughening, the faceting, the mixing, are all trying to reduce this divergent electrostatic energy. So this is fairly well known. This is a paper from 1978, one of the, I guess, the classics, polar heterojunction interfaces by Harrison et al. And they propose that if you have a polar interface, that atomic mixing can solve this problem and take you from this catastrophic increase in the electrostatic potential to a situation where, with the mixed interface, we have a zero average potential and each plane just oscillates around that. So that was, I think, probably one of the first proposed solutions. Another study that was done in the 2000s was on, first of all, literally rock salt, sodium chloride, 111, and later, a few years later, magnesium oxide by different co-authors. And they found surface faceting. So here you see they've, on these diagrams on the top left there, you can see what they're proposing is that the surface layers are smaller than in the films, which means you have smaller electrostatic charge on the surface, and this heals this macroscopic dipole problem. If you look very carefully at the right-hand page, this is magnesium oxide. This is some work done in 2003, and what I particularly like and enjoy about this is not only have they blatantly copied the diagrams from the completely different authors on the left, they've even forgotten to change plus and minus 1 to plus and minus 2 when they move it to magnesium oxide. So there's a lesson in that for all of us. If you're going to copy, do a good job. And there was this fairly high-profile article, Why Some Interfaces Cannot Be Sharp, really highlighting this problem. It is essentially impossible for you to get sharp polar oxide interfaces and surfaces and perfectly ordered films because of this electrostatic problem. So this problem, that every time we add a bilayer we add some constants to potential, this is called the electrostatic catastrophe, and it completely ruins the quality of the films. So if I want to grow MgO 111 on a hexagonal substrate like silicon carbide, I'm scuppered. I can't do it with a clean interface. Or can I? So this is the alternative title of my talk, Hero Hydrogen and the Electrostatic Catastrophe. If you're interested, there is a comic book that goes along with this. Probably more towards an undergraduate audience, but it's quite fun. Here's the idea. If I take exactly the same magnesium oxide film, but on the surface I put hydrogen, what hydrogen brings is a +1 charge, half of the charge that a magnesium layer would add. And if you work through the electrostatics, that essentially kills this macroscopic dipole. So if I can somehow get a magnesium oxide film, I can put hydrogen on the surface and stabilize it. The catch, of course, is how do I get that film in the first place? So what we were thinking then is if we can stabilize a clean polar surface by putting hydrogen on, is it possible in the presence of hydrogen to somehow dynamically stabilize the growth so that we can use hydrogen to create this perfect polar oxide material? So we turn to computer simulations, which is really my strength, putting to hopefully good use the work I did as my PhD. 3 years of hard work, well, 3 years of work, well, 3 years of my life doing density functional theory. So I did warn you that there was going to be some theory. Density functional theory is a lovely theory which tells us that if you want to do quantum mechanics in the ground state, you don't need wave functions. You just need the density. And density is great, because we know about densities. The only catch is at the moment nobody knows how to do it just using the density. So usually the first step is density functional theory, you only need a density. The second step is let's have some wave functions again, which is a bit of a downer, but it turns out they're very simple kind of wave functions. They're just single particle wave functions. And so the equations we have to solve, called the Kohn-Sham equations, are really these things just up here. And this is really just like a single particle Schrödinger equation, just like you would have for a hydrogen atom. And the only difference is that there's this potential here, these VEE and VEN are obviously different from the hydrogen atom. But if we do this and we solve these equations and we get the ground state energy, so that's just the sum of the eigenvalues, and we get the ground state density, so that's just the sum of these mod psi squareds, that's the real ground state energy and the real ground state density of the electron system that we're interested in. But there's a slight wrinkle to how we do this technically, which is, notice the dependencies here. If I'm trying to solve this equation, then I want to know the wave function psi. And the wave function psi is going to depend on all of those terms in the Hamiltonian, and in particular, the electron-electron potential. So I need to know the electron-electron potential to get the wave function. But the electron-electron potential depends on the density. It's a functional of the density. So in typical physicists' unimaginative way, that's why it's density functional theory. So I need to know the density. Once I know the density, I get the potential, and then I get the wave function. So that's fine. How do I get the density? Well, the density I get from the wave functions. And here you see we've got a slight problem, because I don't know the wave functions. That's what I'm trying to do. So I want the wave functions, so I need the potential, so I need the density, so I need the wave functions. So how do I solve it? Basically, we solve it iteratively. We make a guess. We guess the density, and we usually guess that the density of, say, my real system, my magnesium oxide, is just the sum of the atomic densities that you'd get for isolated magnesium and isolated oxygen. So I just put them in the appropriate places in the crystal, add them all up. That's my guess density. Based on that, I compute the potential. And based on the potential, I get the wave functions. Once I've got the wave functions, I can get a new density from them. And then I can get a new potential, and some new wave functions, and some new densities, and a new potential, and a new wave function, and new densities, and I keep going round until I get to the happy state of affairs where the density that I put in, after I've gone through all this sausage factory machine, turning it round, solving it all, getting a wave function, getting a new density, those two densities, the one I put in and the one I get out, are the same. And when they're the same, we've got a self-consistent solution. I've got the right density, I've got the right wave functions, so I've got the right energy. I'm happy. I can go away and rejoice. So that's it. So that's the machinery that's going on in our simulations. And does it work? Well, yes, it does. This is the behavior. This is the change in my estimated ground state energy as I do an iteration round this loop. So I've started it from iteration 2, just even on a log scale, it gets a bit crazy if you start it right from 0. This is the change in energy on my log scale in electron volts per atom, and you can see that it's sort of vaguely linear on a logarithmic scale. So this scheme is converging exponentially towards the ground state. So this is great. This means we can very rapidly get the ground state of my bulk magnesium oxide using these schemes. So this is what we do. We use a computer program called CASTEP, which I'm one of the CASTEP developers, and you know one of the others because it's Stuart Clark here. So hopefully you've heard these terms before. It's a plane wave basis, which means we're dealing with something which needs to be a 3D periodic simulation. We're trying to model the growth of a 2D magnesium oxide film. So that means I need to create a supercell where I have, fine, a 2D periodic slab, and then a vacuum gap, and then there'll be some periodic image, and I have to make sure that vacuum separation is big enough that this is a good approximation to the real system, but that's okay, that's well understood. If you're familiar with DFT, then we're using the PBE exchange correlation functional. If that doesn't mean anything to you, then that doesn't really matter. And what we do is we compute the ground state energies for the different possible sites that the magnesium and the oxygen and the hydrogen can bind to an MgO seed film. And from that, we'll infer the growth process. So here we are. We're going to simulate the growth with homoepitaxial growth. I'm going to say, let's see what can happen. We'll take magnesium oxide. Let's take an oxygen-terminated 1,1,1 surface. It's hexagonal, so I've got 3 crystallographic sites, which I'll fairly boringly call A, B, and C. So the stacking, we hope, just goes A, B, C, and so on. I'm going to put hydrogen on the oxygen surface to stabilize it, and I'm going to ask the following question. If I now try to grow more magnesium oxide, does it grow? Does it bind? Does it grow on top of the hydrogen so that I'd get some kind of film with hydrogen bubbles in there? Does it give me an ordered film, or do I get stacking faults or some kind of weird magnesium hydrides? So here we go. This is what we find. This is my magnesium oxide with hydrogen on. As I bring down a new magnesium layer onto its preferred binding site, it binds to the surface, so it's not repelled by the hydroxyl group, and the hydrogen that's on the surface kind of bubbles up through. So it doesn't stay trapped below the magnesium, but it hops up onto the surface. So that's the first thing. The second thing is it doesn't desorb from the surface. The binding is relatively weak, but even though this is magnesium now on the surface, the hydrogen stays there. The next thing that happens to the hydrogen is it doesn't want to stay in that site. So we started it within the A site. Here, we brought magnesium on the B site. The hydrogen came up, and now the hydrogen moves from its A site across, not on top of the magnesium, but to the remaining empty site, the C site of my crystal. And that gains about half an electron volt per hydrogen atom. So it's relatively favourable. So we end up with this situation. We've got a hydrogen-terminated perfect MgO crystal. Now, if we're getting hydrogen diffusing across the surface, it's all very well to say, oh yes, you gain half an electron volt of energy if you magically remove it from there and put it in there. But can it actually do that? Or is there a diffusion barrier? So we can compute the potential energy surface that hydrogen experiences as we move it along this surface. And here you see, it's sort of pseudo 3D. Hopefully you can see where this is. So now we're looking down on the layer. So I was previously taking this sort of linear cross-section through it, but of course it's a 2D surface in reality. And we can see that whereas I was saying, oh yeah, it moves from this site all the way over to here, which makes it look like there might be a barrier. In fact, if I look at the periodic hydrogen, the one that's over here, we can see that actually it can slide the other way straight down into this C site. There's a potential well here, this is the favourable site, and there's no barrier. So we expect that once the hydrogen has moved up to the surface, it will immediately diffuse down, releasing half an electron volt of energy per hydrogen. So we end up with an MgO film, Mg terminated surface with hydrogen. So what happens next? Well, of course, we want to look at an oxygen layer. So oxygen comes down. Now we've got an odd situation because the oxygen is coming down onto its favoured site, but hydrogen is already there. So what happens? It turns out what happens is as the oxygen approaches the surface, it binds to the hydrogen, but this new hydroxyl group then flips and rotates round. So even though the oxygen is coming down, even in the worst possible case, when the oxygen comes head on, right down onto this hydrogen, and the hydrogen is sitting where it wants to be, the hydroxyl group will still rotate round to leave me with MgO surface, just like we started, hydrogen terminated. So in the presence of hydrogen, there is, according to the simulations, a mechanism for adding a bilayer of MgO, growing the film perfectly with no problems due to the electrostatics. Now, of course, the problem is if this hydroxyl does not rotate, we've got hydrogen trapped in the material again, and I've got some weird hydroxyl, magnesium hydride, magnesium hydroxide. So we need to know, is there a barrier to this flipping? So to study this, all we did is move the oxygen in our simulation step by step. Rather than letting it just go where it wants to, actually drag it down, drag it down, drag it down, look at what happens to the hydrogen. And we get a series then of potential energy curves for each oxygen position. So these different curves are for different oxygen positions. As I take the oxygen, this purplish one, this is the oxygen quite a long way away, nearly 5 angstroms from the surface. And along here we're saying, how does the energy of the hydrogen vary if I just pull the hydrogen away and make it flip? And you can see that when the oxygen is a long way from the surface, I get this purple line, and there's a big barrier. There's a 2 electron volt barrier to this flipping. But as I move the oxygen closer and closer to the surface, I move into these further lines, and when I get to the green line, you see that this barrier here has disappeared. This green line is only at about 3 angstroms, so it's still a relatively long way from the surface. And as I move the oxygen towards its preferred binding distance, I get not only is there a very strong tendency for the hydrogen to come off, there is no barrier to it doing so. And this ends up releasing about 2 electron volts of energy. So it's very strongly favoured. So we end up with a perfect magnesium oxide bilayer. The dipole is healed not just statically at the perfect surface, but dynamically during the growth process. Hydrogen is acting as a surfactant. It's not desorbing from the surface, nor is it becoming trapped in the film. At every stage, the hydrogen is coming up and staying on the surface. Now, the simulations were not without their problems. It turns out, as we study this growth dynamically over more than one bilayer, the bigger the film we study, the more iterations our simulation took to converge. And this gets to be a problem, because as I add more atoms, of course, every iteration is getting more expensive. I've got more electrons to figure out where they go. So I'm already paying a price for having more material. I don't want to pay a price just because it's a bigger simulation. In fact, when we investigated this, even if we take exactly the same film, not making the film any thicker at all, but just increasing the simulation cell, so increasing the vacuum gap, we take more iterations to converge. And this is what we found. If I take a slab and I go from bulk, so from a 0 angstrom vacuum gap, and I increase the vacuum gap, the iterations go from the sort of 8 to 9 that I showed you for the method earlier, roughly linearly, and end up 2.5 times as expensive. Now, you could argue that in this sort of region, well, of course, you're changing the physics. I'm going from a bulk magnesium oxide cell to some 2D slab with a dipole moment, and you might expect the number of iterations will change. It's a different physical problem. But once I've got past somewhere around here, you would expect the physics ought to be the same. I've got a fairly isolated slab. Why is it taking more iterations for my method? And more importantly, can we do something about it? The first question we wanted to ask is, well, is it just magnesium oxide? Well, no, it isn't. So we chose everybody's favourite material, graphene. And we said, well, does this happen for another sort of 2D layer where we want to have a vacuum separation? And as you can see, yes, it does. So here's graphene going from the 3 angstrom graphite, multi-layer graphene. As we increase the vacuum separation, you never get funding for graphite, do you? But multi-layer graphene, that's a hot topic. So here we go. So like you, I'm sure all my pencils I now refer to as multi-layer graphene. When I'm talking to my undergraduates, they get very excited about that, and they think I've made some breakthrough technology. you can see that as I split my multi-layer graphene into isolated single layers of graphene, I get this linear degradation in the performance of my simulation methods. Is there something about 2D sort of systems? Here's a 0D system, a gold nanocluster. So this is really from sort of biophysics point of view. Gold is interesting. This is a very small nanocluster. I think this was a tetramer, just a sort of proof of whether it happened here. So we've got a sort of quasi-0D system, and I'm now expanding the vacuum in all the directions, and again we get this linear degradation in the performance. So this sounds like really bad news. This sounds like whatever I do with my lovely CASTEP code, the bigger the system I give it, the more effort I'm going to have to do in the iterations, let alone the fact that my iterations themselves are going to take longer. Now, we're physicists, so we don't just throw our hands up. We say, well, why is this happening? So it turns out that the problematic term is this electron-electron repulsion term. And if we look at that in Fourier space, the electron-electron potential, we call the Hartree potential normally, basically it's proportional to the density in reciprocal space divided by the modulus squared of the wave vector. So if I have some guess density, there's some error in there. So the error in my potential is, in Fourier space, is the error in my density divided by mod wave vector squared. And now we start to see what goes wrong when I have a big real space cell. Because if I have a big real space cell, I have some wave vectors that are really, really tiny. Which means I've got an error in my density divided by a really tiny number squared. So I come into my lovely iterative method with a small error in the density here. A small error in the density now leads to a large error in my potential, which means I've got a bad Schrödinger equation. So I'm going to get a large error in my solutions. And they're the very solutions I'm using to construct my next density. So of course I don't have a well-convergent scheme, because I start with a small error and I get, after one iteration, a big error. This is not a recipe for success. So what can we do about it? Well, what we're going to do instead is we're going to model the Kohn-Sham equations with a different equation that is cheaper to solve, and therefore we can solve much more carefully with more advanced and sophisticated techniques. And this is the model functional that we're proposing. I'm going to take the Hamiltonian from my Kohn-Sham equations, essentially, and I'm going to apply it not to the wave function, but to the square root of the density. So this is really what's known as the Pauli potential approach. So in papers in this field, they usually start with, it is well known that the square root of the electron density obeys a Schrödinger-like equation. I'd never come across this. I don't know whether you have, but apparently this is well known. But if we use this as a model for my system, now I have to solve this Schrödinger-like equation for only one object of one wave function-like object, not one per state, just one of them. So I can solve it very carefully. I can solve it deliberately looking at this change in the potential as I change my density and trying to reduce the problems of this instability in my model system. Once I've solved the model system, that suggests a new density to put in to my main Kohn-Sham system. So we've now got a kind of a coupled method where I very carefully solve a model functional that I can solve exactly, and I use that solution to go back into my Kohn-Sham. So I put submitted here. Actually, that was supposed to be submitted on Monday, but it wasn't. So it's nearly submitted. But either way, if you're interested, there is a manuscript you can look at. So, of course, the next question is, does it work? And the answer, of course, is yes, or why would I be standing here telling you about it? So here we are. This is the standard technique, and this is what happens with this method. So you notice if I go from bulk magnesium oxide, from the bulk to the surface, the number of iterations does increase. The physics has changed. I've gone to a slab geometry. But once I've got a relatively well-isolated slab, and I expect the physics to be pretty much constant, as I increase the vacuum gap from sort of 4 angstroms all the way up to 10 angstroms, the algorithm behaves exactly as we hope. The real physics hasn't changed. The algorithm takes the same number of iterations to converge. Is this magic about magnesium oxide? Well, let's go back to our graphene. This was the previous convergence. This is the convergence with this method. Again, flat convergence, same number of iterations regardless of the separation. And finally, the gold nanocluster. Again, some noise on this. Obviously, this is discretized. You can't have half an iteration, so there is expected to be some shot noise. But to a reasonable approximation, we've got a flat, constant performance. So when I go to bigger and bigger and bigger systems, I don't care. It takes the same number of iterations to converge. Right, so we've fixed our simulations, so now we can use them. And we can simulate full layer-by-layer growth for as many bilayers as we like. Now, I haven't got time to go into the full process there, but essentially, nothing changes. The dipole does not diverge. The hydrogen on the surface suppresses the divergent dipole. And the mechanism is exactly as I've explained for one bilayer, just rinse and repeat. And we can grow in our simulations macroscopically thick films, except that we run out of computer time, but you can grow a lot of it. Certainly until you get bored and EPSERC start asking questions about why you're wasting their computer time. So here's our proposed mechanism. We start with MgO, an oxygen-terminated surface with hydrogen on. As we bring an Mg layer down, it binds, hydrogen moves up to the surface and across to a different binding site. Then an oxygen layer comes down, the hydrogen and oxygen flip, and I'm left with magnesium oxide, oxygen terminated, with this hydrogen surfactant, just as we were. Perfect film growth. And if you're interested in seeing a little more about that, then there's a PRL we did a year and a bit ago now. So, key characteristics: hydrogen heals the dipole, promotes perfect ordering, is not trapped. The question, of course, is, am I just telling you what Castep-Land says, perfect Castep-Land polar oxide, or am I telling you something that really happens? So, one hydrogen cracker later, here is MgO on silicon carbide in the presence of hydrogen. You can see we've got a nice well-ordered silicon carbide. This is silicon carbide 6H. We have no particular reason to think that matters. And you can see you've got the little zigzag hexagons, and you can see that the surface between the silicon carbide and the MgO is sharp, and the film is very well ordered. If we zoom in and look at the interface itself, again, we see here's our silicon carbide, here's our interface, here's very well, atomically sharp interface, very well ordered magnesium oxide in the polar direction. So, I hope I've convinced you that I have a shed load of these if you're not convinced yet, but an hour of electron microscope images doesn't really float my boat. Maybe it does with you, but we'll talk later. I certainly have people who would get on with you very well if that's your idea of fun. The question then is, okay, I can get this perfect polar oxide, but is it because of the hydrogen? Or is it just fluke? So how can you see hydrogen? Well, annoyingly, of course, hydrogen's fairly electron transparent, a bit difficult to pick up on a microscope, but we could do XPS. So here's an XPS. Binding energy against intensity, and we see that there's a shoulder here, and this shoulder, if you fit it to the sort of Gaussian envelopes, we get a Gaussian here right on the expected OH binding resonance. So, just to hammer it home, here's the film diffraction spot saying, yes, it's really ordered. You can get diffraction and all sorts of interesting things. Here is some more XPS data, and my colleague Vlado Lazarov has published some of this in a PRB 7 years ago, showing that this happened accidentally in some of their films. They just noticed that they had this bump in the films that were better ordered. And if you're interested, on the right-hand side, you can also see that the OH-terminated surface is the one that has the closest local density of states to the bulk magnesium oxide. So not only do we get perfect film growth, but actually the OH surface is also not disrupting the electronic properties as much as either a magnesium or an oxygen terminated surface, which is a happy coincidence. Right, so if we're going to want to use these things, I've shown we can grow magnesium oxide on silicon carbide, but I started saying we wanted to make some devices out of this thing. So what are the properties? And the properties that we've looked at so far are mostly the band offset. So what happens if I have silicon carbide and I stick MgO on it? Now you'd think you could just go away and measure this. Well, you can. Here's somebody who claimed to do a very careful measurement and get a valence band offset of 3.65 eV. Here's somebody else who claimed to have done a very careful measurement and got a valence band offset of 1.5 eV. Other workers have done what they claim are very careful measurements and got 1 eV. So we have a 3.6 times variation in the valence band offset. Well, it's great as a theorist. It means whatever we get, it's bound to match some experiment. But it would be quite nice if we could figure out what's going on, because these are relatively well-respected groups, and we don't think they've screwed up the experiment. So why are they getting this variation? Now, one thing is that the one on the left is on silicon carbide 4H, not 6H, but this doesn't normally change very much. You might look at 1/10 of an eV, but certainly not 2.5 eV. So okay, fine. Let's simulate it. Let's see what we get. So we simulate it. Here we have the mean electrostatic potential as they go from our 6H through an interface region to our polar MgO111. These are the valence band maxima in the respective halves with respect to the mean electrostatic potential, and we get a valence band offset of 2.4 eV, which matches none of the experiments. But we can wave our hands and go, oh, it's in the middle. That's not very satisfactory. So that doesn't really explain anything very much. Now, it's well known that when you do density functional theory, the alignment of bands is very, very, very sensitive to how you approximate the electron exchange correlation, because we don't actually know what that is. Density functional theory says there's an exact one out there, but it doesn't tell you what it is. So we just make some educated physical guesses. Is that all we can do? Are we stuck? Well, we're not. We can use many-body perturbation theory, usually in the GW approximation, and we can say, right, so can we go a little bit beyond density functional theory, use a more expensive, computationally intensive method, and see what happens? And the answer is you can for the bulk materials. You can't do it for the interface. But it turns out that the valence band maxima of the materials are, even in the interface, are dominated by the bulk. So if we do that, what we find is our valence band offset goes from 2.4 eV to 3.5 eV, which is pretty much within expected error of the 3.65 eV measurement. So it is possible to understand this. Now, I should say this is what happens if you take silicon carbide and you put MgO on, starting with a magnesium layer. And this was attained at great computational expense, which got us wondering whether there was a way we could do it at slightly less computational expense. Talking to our friend Professor Clark here, we thought we'd try screened exchange. Screened exchange is a way of going a little beyond DFT, but not all the way to many-body perturbation theory. And this is what we get. It looks pretty much indistinguishable from the GW result. If I go back to the GW, you'll see the GW has a valence band offset of 3.5 eV. This gives us 3.4 eV, but is 10 to 100 times faster to compute. So this looks like this might be a winner. This method will give us pretty accurate valence band offsets at a fraction of the expense of a full many-body perturbation theory calculation. Plus, there are actually good codes, efficient codes, that do screened exchange in a DFT kind of fashion, and there aren't yet GW. He says, looking at a man in the audience who's implementing GW in CASTEP. So we can understand where offsets of 3.5, 3.6 EV come from. Why are some of them getting 1 EV? Well, it turns out if you put oxygen as the first layer instead of magnesium, and you do, I've called it the DFT band offset, it's actually the GW band offset. If you do the GW band offset, I get a valence band offset of 1.01 electron volts. So what we think is happening is very, very simple. When you grow magnesium oxide, generally, you're doing layer by layer deposition, but if you don't control which layer comes first, you might get a magnesium layer, you might get an oxygen layer. If you're not careful, you might get a mix. They usually sort themselves out if you're in the boundaries. So if you have oxygen as your first layer, you get a 1 EV band offset. If you have magnesium, you get 3.5 EV. So this is good, and the experimental groups have largely accepted this, mostly because we've told them they've probably got well-ordered films and get close to our theoretically ideal offsets. It's just they've got different interfaces. Everybody's happy, except the people who get 1.5 EV. We haven't got time to go into that today, but it turns out if I stick a thin layer of silicon dioxide in between silicon carbide and MgO, I get 1.5 EV. They're less happy, those experimental groups. They don't like our work. But hand on heart, I think that's what's going on. I think if you get, we're only modeling 1 unit cell of quartz. It really is not a massive oxidation that you require to shift the valence band offset by half an EV. But obviously, if you're a UHV growth group and you can't grow non-oxidized surfaces, or at least think to check before you measure valence band offsets, well, they don't like that suggestion. Let's just leave it at that. Right, I better finish up there. So the conclusions, 3 main conclusions for the first third, the middle third, and the last third. So hydrogen can dynamically stabilize polar oxide growth. Independently, this has been verified in zinc oxide, which is, as a transparent conducting oxide, rather more interesting hot topic than magnesium oxide. So I do think this is a general mechanism. There really is nothing in the simulations that's specific to MgO anyway. That's why we chose MgO. Our simulation methodology we can improve using this auxiliary sort of model functional method to rapidly perform simulations on large nanostructures. And of course everybody wants to do nanomaterials. That's the holy grail, because everyone knows nano is Greek for funding. And the final conclusion is that yes, DFT has some problems with common approximations, getting band gaps and band alignments right, but going a little bit beyond DFT, so most of what I've done so far has been GW, but it's very promising using screened exchange methods, we can accurately model the band offsets, and they really do seem to be accurate. Unless there's some complete fluke that all of our errors match all of the experimental errors, we're getting within 0.01 volt in band offset for the oxygen terminated surface. So it's really, I wouldn't like to say we'll always do that, but we're certainly getting beyond qualitative accuracy and towards quantitative agreement. Finally, I should acknowledge my collaborators. So in York, Matt Probert, who I work on the CASTEP development and simulation side. Vlado Lazarov, who does a little bit of modeling but is mostly an electron microscopist. From the European Theoretical Spectroscopy Facility, Martin Stankovsky and Andrei Schliefer, so they helped with some of the GW calculations and also with some other hybrid functionals. The United Kingdom Car Parnella Consortium, because they pay me, so particular thanks to them. And if you'd like to know more particularly about the MgO group, there's the reference again for the PRL. Thank you very much for your attention.